How to implement the BFS or breadth-first-search algorithm in Python. Hi, in this video, we'll start with a short preview of how the BFS algorithm works. Then we'll continue to the implementation part of the algorithm in Python. At the end, we'll run some tests to make sure that our code works as expected. Let's begin with a preview of how the BFS algorithm works. The algorithm receives two parameters. The first one is a root node. From the root node, we are able to travel to any other node in the graph. If it's not possible, meaning the graph is not connected, we'll receive multiple routes. Second parameter is the value or target value that we're searching for. Let's say in our example, it's 7. We'll also use two data structures in our algorithm. The first one is a queue that will allow us to process the nodes in an ordered way. And the second one is a set that will allow us to track which nodes have reprocessed, so we make sure to process each node one time and one time only. We'll add the root node to the queue, and we'll also add the root node to the set. Then we pop the leftmost item from the queue, which is 0, and then we'll add all of its neighbors if they're not in the set that tracks which nodes we have visited into the queue. So we'll add 1, 4, 2, and 5 in that order. 1, 4, 2, and 5. And we'll also add them to the set. 1, 4, 2, and 5. Then we pop the leftmost item from the queue, and we add all of its neighbors if they're not in the set. But 4 is already in the set, so we have nothing to do. Next, we process the leftmost item, which is 4, and we add all of its neighbors if they're not in the set. But all of its neighbors, 1, 0, and 2, are in the set, so we have nothing to do. Then we pop the leftmost item from the queue, which is 2, and we add all of its neighbors that are not in the set, which is only 3. So we'll add 3 to the queue, and we'll add 3 to the set. Then we pop the leftmost item, which is 5, and add all of its neighbors that we have not tracked so far, which is 6. Oh, I forgot to mark 0 and 2. So for 5, we'll add 6 to the queue, and then we'll add 6 to the set. Next, we'll pop the leftmost item, which is 3, and add 8 to the queue from the right, and also to the set. Then we'll pop 6 from the queue. Look at its neighbors. Oh, and we have found 7, meaning 7 is found in the graph, and it's reachable from 0. Okay, now let's move on to coding the algorithm. So let's implement the BFS function. The function receives two parameters. One is a list of nodes called routes. We expect a list of nodes and not only one node or one root, because the graph could be made of several connected graphs, like this one, and we want to receive a root for each one of the connected parts. The second parameter is a target value of type int, and we want to return a node from our function. Now, let's initialize two data structures that were mentioned earlier. One is a queue and one is a set. For the queue, we want to use Python's collections library that has an implementation of a dequeue. Queue in Python is used for working with threads, so we'll use the dequeue instead. But we'll call only the matching functions that exist for a queue as well. So let's initialize the queue. Queue equals dequeue, and we'll initialize it with the list of roots. And we want to initialize a set, and we'll call it scene, and we'll initialize it with the list of roots as well. Now we want to run our algorithm as long as there are nodes or elements in our queue. And every time we want to pop an element from the queue from the left, so node equals queue dot pop left, and we want to make sure that the node is not none. If not node, just continue. And then let's see if the node contains the target value. If node value equals target value, then we found the node. Now, if we didn't find the target value, let's add all of the node's neighbors to the queue. So for neighbor in node neighbors, if neighbor not in scene, because we don't want to process a node more than once, then let's add it to the queue. No, the neighbor. And we also add to the set the neighbor. And at the end, if we didn't find our target value in the graph, we just want to return none. Okay, for the time and space complexities, so for the time complexity, as we mentioned earlier, we can add or we can append elements to the queue and pop them from the beginning with O of 1 time complexity. And for adding elements to a set or checking if an element is in a set, it costs us O of 1. So the time complexity is adding all of the elements to the set, that's O of n, and also we have to go through all of the edges in our graph. So the total would be O of Vn plus E, where V is the nodes in graph and E is the edges in graph. For the space complexity, we only store the nodes in our scene sets, or we store all of our nodes at the queue at once, so the space complexity is O of V. And now let's test our code. So I prepared in advance a graph, and we create a graph with 12 nodes, and we want to return the node of 0 and node of 9. And actually, this is the graph I'm talking about, and we saw it earlier. I'll put it on the right, and we want to run our BFS function. So remember, we have two routes that we start our search from, 0 and 9, and in the following cases, we'll look for the target values of 0, 1, 7, 9, and 11. 0, 1, 7, 9, and 11, and they are all reachable from our routes. But 15 and 33 do not exist in our graph, so we expect to return none for these cases. So now let's run our code. Perfect, and as expected, we did receive the nodes that we were looking for, but received none for the non-existing values. Okay, thank you very much for watching this video. If you found it valuable, please like it and subscribe to my channel, and see you next time.